So can you hear me on the stream? Not only on the tutorial, on the stream as well?
Yes.
Right. Okay. Good.
Yes, perfect.
Right. So my talk is going to be slightly different from the previous ones because I'm going to talk about higher curvature theories of gravity, but not as the gravitational theory of the universe, but rather as a tool for doing condensed matter physics and also for doing field theory. Okay. So basically, the problem is the following, right? So this is within the context of the AdS-CFT correspondence. So you may have heard of this topic. It's like a hot topic in high energy physics. So basically, the idea is that under certain circumstances, a gravitational theory can be used as a way of obtaining the generating functional for correlators in a field theory with conformal symmetry. Okay, this is the main point. Right. So now, why this is interesting? It's because the work that I'm going to present is within the context of just classical gravity, right? So the tools may be interesting for doing gravitational computations. Okay. So let me just briefly summarize what the point is of the AdS-CFT correspondence. So if I had to summarize this in one slide, basically the idea would be the following: that for gravitational theories on an anti-de Sitter background, so that means with a negative cosmological constant, the gravitational action computes the correlation function, the generating function for correlation functions of a field theory. Okay, and in this interpretation, the boundary values of the bulk fields are what are taken as the currents, so the sources, right, of the field theory. Okay, so the duality, basically, this is AdS-CFT duality. The duality is within the boundary values of the fields in the bulk theory of gravity and the sources, the external currents in the side of the field theory. So then you can generate the correlation functions just by taking functional derivatives of the classical gravity action. So functional derivatives of the classical gravity action with respect to these boundary values. Okay, okay, good. But now there is a problem with this that is basically what my work deals with. Okay, so the point is the following: you can expand like an anti-de Sitter metric, an asymptotically anti-de Sitter metric in this way. Okay, so this is what's called the Pompare patch, right? So basically, in anti-de Sitter spacetime, the line element, so the metric interval, right, diverges near what's called the conformal boundary. So this basically means that when you have an anti-de Sitter space, which is the Euclidean section of it is like a saddle, right? So it has infinite volume. It is an open universe, right? So the volume element diverges the closer you are to the conformal boundary. Okay. However, if you want to use the gravity action as a tool, as a generating function for correlators, you need it to be finite. Okay, so you need to have a way of canceling the divergence of the line element. Okay, but this has to be done in a way that it respects the variational principle for the gravity action. So this is crucial because you want to have an object that you can take functional derivatives with respect to the field content. So you need the variation of the action to be a total variation of the values of the fields, right? So it has to have a Dirichlet variational principle in the sense that the total variation of the action has to give you the equation of motion, which on shell are identically zero, plus a boundary term that can be written as a total variation in terms of the boundary values of the field. Okay, so this is what's a Dirichlet. This is called the Dirichlet boundary condition. Okay, so this is what you have to do. So you need to find a way of making your action finite, respecting the variational principle, in order for the functional variation of the action with respect to any of the bulk fields to be written as an entire variation of the boundary value of the fields. Right. So in this duality, basically, like a concrete example, the boundary metric. So this is the metric at near the conformal boundary, near z equal to 0, is interpreted, for instance, as the source, as the external source of the energy momentum tensor of the field theory. Okay, and for instance, other boundary values of other fields are interpreted as the holographic sources of the associated operators in the field theory. Okay, so this is the setup. Okay, so now how do we go about fixing this problem? Okay, so essentially, this is the gravity theory that we're going to consider. So by higher curvature gravity, like there were previous talks where for instance, the Gauss-Bonnet gravity was discussed. Okay, so Gauss-Bonnet gravity is like an example of higher curvature gravity. So essentially, it is any gravitational theory whose Lagrangian density can be written in terms of the Riemannian curvature only. So all possible contractions of Riemannian curvature to an arbitrary power. This is what's called the higher curvature gravity theory. And the equation of motion of a generic higher curvature gravity theory, it is given by this. So this is the equation of motion tensor, which should be equated to 0, right? So the variation of the action basically gives you the equation of motion tensor in the bulk times the variation of the bulk metric plus a boundary term, right? Just like in the standard thing in classical mechanics. So if you want the variation to be equal to 0, you need to have two things. You need to have the boundary condition, but then in the bulk you get the equation of motion equal to 0, right? So essentially, okay, this is the generic equation of motion for all these kind of theories. And now the point is that without needing to specify the theory, you can analyze the divergent structure of the action. So this is the main point. The main point is that without needing to fix the particular theory, it is possible to say generic things about the kinds of divergences that the action has near the conformal boundary, which is needed in order to subtract these divergences and make the action finite. Okay. So how can this be done? So essentially, just by considering symmetry, the Riemann tensor can be expanded in powers of the holographic coordinate. Maybe I should emphasize this a little bit better. So in this metric, okay, this is a metric with one more bulk dimension, right? So this one higher bulk dimension is what's called the holographic radial coordinate, right? So the theory that describes like the condensed matter system, your quantum theory, lives at the boundary, so it lives in one dimension less, right? So this is what's called the realization of the holographic principle. So essentially, the boundary theory lives in one dimension less, and the metric in the bulk, where you're embedding your boundary theory, has this extra radial coordinate, which from the side of the condensed matter system is interpreted as the energy scale. Okay, so this is the coordinate z. Right, so you can expand your metric just like you can do in general, right? You can expand it in terms of this radial coordinate, like the holographic coordinate, and the coordinates that are tangent to it. Okay, so this is like the boundary metric at different values of z, right? And then the boundary metric, you can expand it as a power series in terms of this radial coordinate, such that near the z going to 0 boundary, essentially the boundary term that is leading, so the one that sources the leading term in the boundary is this G naught. Okay, so this is the leading order term in the expansion of the boundary metric in terms of the holographic coordinate. Okay, so this is what's interpreted as the source of the energy momentum tensor. Okay, so now going back, so basically what you can do is that just by the symmetries of the Riemann tensor, right? You know that if you plug the previous expansion of the metric, you plug it into the Riemann tensor and you compute up to the linear order in Z, in the holographic radial coordinate, this is the form that the metric will have. This is just taking the previous expansion, plugging it into the Riemann, and you get this, okay, plus higher order terms. So first we're going to constrain the linear order. Okay, first we're going to constrain the linear order, so you can do that with the Riemann, and now this tensor P, which is the variation of the Lagrangian with respect to the Riemann, okay, has the same symmetries of the Riemann, so it can be written in this form in terms of arbitrary constants. that of course will depend on the particular theory, okay? But generically, just by taking this form of the Riemann and the P and plugging it back into the equation of motion, you can get the following expansion in terms of the radial components and the tangential components of the equation of motion tensor, okay? And the equation of motion is these two tensors equal to 0, okay? So from here, you can see that just by symmetry arguments, the G1, so the linear term of the metric has to be equal to 0, right? So the equation of motion for generic higher curvature gravity constrains the G1 term to be equal to 0, okay? Well, unless some particular fine-tunings happen with respect to the couplings of the higher curvature terms, but in the generic case, the equation of motion constrains this to be equal to 0, okay? You can continue this argument to the next orders, and you will find that the G2 has a universal form that is independent of the theory that you're considering, and the G3 is also constrained to be equal to 0 by the same symmetry arguments, okay? So knowing this, you just need to plug it back into the Lagrangian, right, in order to find what is the divergence structure of the generic gravity action, and you will see that it is the same divergence structure than the one that you have for Einstein gravity. This means that in the holographic context, regardless of which higher curvature gravity you're considering, as long as you're considering up to 5 dimensions, and that therefore you only need to expand up to cubic order in the holographic radial coordinate, the divergence structure will be the same for any higher curvature gravity theory. Okay, so then you can basically apply the same renormalization methods that you use for Einstein gravity to any other gravity theory, and in particular, you can use this procedure which is called the counterterm procedure with K, so it's an extrinsic counterterm procedure, and the details you can find in this paper. So the moral of the story is that the divergence structure of a higher curvature gravity action is the same than for Einstein gravity when you evaluate it in an anti-de-Sitter bulk of up to 5 dimensions, and this allows you to cancel the divergences and obtain a finite generating functional for the CFT. Thank you very much. Yeah, so okay, that's a good question. So you can think of this in two ways, right? Either you can say that you're trying to describe like a quantum mechanical system, some field theory in the boundary, right? Because like you can say, okay, I'm using gravity as a tool because I know how to do gravitational computations, which are classical, which are easier, let's say. And then you can say something about quantum correlators of some field theory that may be hard to compute. This is one way of seeing it. And the other one is like you're saying, like you can also run the game in reverse. You can say, we can imagine that you just have a quantum theory in the boundary, and that the gravitational description of the system in one dimension higher is just like an emergent property of the quantum behavior of this condensed matter system that exists in one dimension less. You can think of it the two ways, right? It's a duality. So you can either think that gravity is emergent from some like computational process that happens in a field theory in the boundary, or you can think of this the way that I'm doing here is that the gravity is just used as a tool, as a computational tool, in order to do some standard computations of a field theory system, like computing correlators and things like that. Right, thank you.